Hello, everyone. Thank you for attending this talk. I'm Rathijit from Microsoft, and together with my colleague Vishal, we'll be presenting about predicting optimal parallelism for data analytics. Here is the structure of our talk. First, we'll present a general overview of the problem. Then we'll give a brief overview of 4 case studies: AutoDOP, AutoToken, Task, and AutoExecutor. Finally, we will conclude with a couple of open research questions in this area. Cloud computing platforms provide opportunities to users to provision resources dynamically in a fine-grained manner as much as is needed. Cloud service providers also provision their cluster capacities according to resource demand and utilization. A question is, how much resources does a job actually need to have to meet its cost and performance objectives? And in this talk, we focus on automatically predicting the optimal parallelism for jobs and the computational resources that it needs. We also want to allow flexibility in choosing the optimal operating point depending on the cost and performance objectives, and to provision resources accordingly. Our approach is to predict the job's peak parallelism as a function of its characteristics, or a job's runtime as a function of its characteristics and amount of parallelism. In this talk, by a job, we mean an analytics query, and we'll be using the term job and query interchangeably. Why we are interested in peak parallelism is that ideally, at that point, the job would have the lowest runtime, and any further resource allocation would be wasteful. But we may be able to achieve the same runtime at a lower amount of parallelism, and in some cases, if there are overheads associated with high parallelism, we might actually be able to improve the runtime at lower parallelisms. For query characteristics, we are interested in compile time and optimization time properties and estimates. This is because we want to do the prediction for the queries before they have run. So at that time, the runtime properties are not available. And we learn this function f using machine learning models on past executions. So this is the general framework, and we'll be seeing this over and over again in the case studies that we discuss next. So here is a quick summary of the case studies. They differ according to the platform, the number of nodes involved in the operations, and the type of predictions. We'll be explaining these concepts as we go along. One of the concepts that will appear is that of the performance characteristic curve, or PCC, which shows a plot of the relationship between the runtime and the parallelism. And we want to provide such a view to the user so that they can select the optimal operating point to meet cost and performance objectives. So now I will start with the first case study, which is AutoDOP on SQL Server. This is joint work with my collaborators at the University of Wisconsin-Madison, and more information is available in these papers. In this AutoDOP project, we have focused on SQL Server running on a single node. For every query, we can specify the degree of parallelism, or DOP, which is the maximum number of threads that can be active at any time for executing the query. And depending on this choice of query, this choice of DOP, the query runtime could be affected, and hence also its cost. And this can also affect the resource utilization and provisioning in cloud computing platforms. The choice of the DOP value affects different queries in different ways. Here we show a few example queries from TPC-DS benchmark suite. The x-axis shows the degree of parallelism, or DOP, and the y-axis shows query runtime normalized to the runtime at DOP1. Some queries are well parallelizable, that is, their runtimes decrease with increasing DOP. Whereas for some other queries, they're not so much parallelizable, particularly at the high DOPs, and we see that actually the runtime increases at high DOPs. So from these examples, we see that a single choice of the DOP is not likely to be optimal for all queries, and we need to take into account query characteristics while selecting the optimal DOP. The choice of the optimal DOP also depends on the amount of data that the query processes. Here we show 6 workloads from TPC-DS and TPC-H, and for different scale factors. So on the x-axis, the term DS means TPC-DS and H means TPC-H, and the numbers indicate the scale factor. So DS100 is on scale factor 100, whereas DS1000 shows TPC-DS 1000, which is on scale factor 1000, and it processes about 10 times as much data as DS100. Within each bar, the colors represent the percentage of queries that have that value of the optimal DOP, and the legend shows those optimal DOP values, so 1, 8, 16, 20, 32, 40, 64, and 80. As we have discussed previously, for any workload, there isn't a single DOP value that's optimal for all queries. Rather, there is a mix of optimal DOP values. Moreover, we see that as the scale factor increases, that is, as the data set sizes increases, the higher DOP values become optimal for a larger fraction of the queries. For example, at DS1000, more queries have a DOP 80 as optimal than at DS100. Similarly, for TPCH 1000, there is a higher percentage of queries with 80 as optimal DOP than at TPCH 100. So we need to take into account the data size as well while selecting the optimal DOP. So our approach is to use the query characteristics such as query plan operators and then estimates of the data sizes, the cardinality number of tuples processed, and so on. And then given a target DOP, we use machine learning models such as random forest to predict the runtime at that DOP. And once we have the runtime at different DOPs, we can select the optimal DOP. For the machine learning models, we use a regression model to first predict the runtime and then select the DOP instead of using a classification model to directly select the DOP. Because with the regression approach, we can have a richer selection of the optimization objectives and we can select the operating point accordingly. Here are some example results from subsets of queries taken from TPC-DS benchmark suites. We show two test suites, test 1 and test 2. For each test, we consider the sum of query runtimes over all the queries in that test. And for the baseline, we consider all queries executing at DOP 64, which is the default value for our system. A speed up of 1 means no performance change, greater than 1 means performance improvement, and less than 1 means performance loss. For each test, the third, fourth, and fifth series are with policies where all the queries are running with the same DOP value. So workload optimal means all queries with the DOP that's optimal for the entire test suite. And 40 and 80 means all queries at DOP 40 and 80 respectively. Query optimal means each query has been given its optimal value of DOP, and it shows a speed up over workload optimal. However, both query optimal and workload optimal assume the existence of an oracle which accurately selects the correct DOP, but this may not be realizable in practice. So the first series, which shows ML, is actually from the auto DOP predictions, and we can see that with those values, we can get speedups that are closer to the query optimal policies than with the static selection policies. We will now move over to the next two case studies, AutoToken and task. While AutoDOP predicted the runtime for each DOP value, AutoToken will predict the peak parallelism, and then Vishal will be talking about the task project which predicts both runtime and PCC. So I'll start with AutoToken. This is joint work with my colleagues at Microsoft, and more information is available in this paper. In this project, we looked at the execution of scope queries on Cosmos, which is our exabyte scale big data analytics platform at Microsoft. On this platform, the unit of resource allocation is a token, and a token consists of a number of cores and amount of memory. Tokens can be of two types, guaranteed and spare tokens. Spare tokens are allocated dynamically as the job runs, depending on available cluster capacity. In this work, we focused on provisioning of guaranteed tokens. And the number of tokens allocated to a job may affect its runtime and hence its cost, as well as resource utilization and provisioning decisions. The AutoToken project focuses on predicting the token count so that the job can achieve its peak parallelism. So it looks at peak resource provisioning. Any more tokens would be wasteful because the job performance would not improve. And then the jobs would also need to wait unnecessarily to get those tokens. On the other hand, with less tokens, there could be a loss of performance, or the performance could be unpredictable, particularly if the job is relying on the availability of spare tokens for performance. Now, given a job, how would a user select this token count? They could use a guess, or they could use a default value or a default percentage for the VC or virtual cluster. But we have seen on our clusters that this policy is quite suboptimal. So this chart shows the distribution of the ratio of the requested token count divided by the peak token count on 5 of our production clusters. A value of 1 means perfect allocation, whereas greater than 1 means the job is over-allocated, and less than 1 means it is under-allocated. And as you can see on our clusters, 40 to 60% of jobs are over-allocated. And this is the space that AutoToken tries to focus on to reduce this over-allocation for the jobs. This figure shows the skyline of an example job where the x-axis shows runtime and the y-axis shows resources or the tokens used. And here, as we can see, the default allocation is much more than the peak requirement. So this job is over-allocated, and we want to go towards this ideal allocation. So that's what AutoToken aims to do. It tries to eliminate this over-allocation, and there would be no performance impact ideally because these tokens are not going to be used. Our approach to do this is to use machine learning models to learn the peak token counts from past behavior. So we group jobs by their characteristics, and we use signatures for grouping these jobs. And then we build ML models for each job group. When a new job arrives, we compute its signature and see if for the corresponding group, a model has been built. And if so, we use that model to predict the peak token count for that job. Here are some example results. So as we can see on the chart, with AutoToken predictions, the distributions of the requested token count divided with the actual peak token counts are closer to the ideal value. So that is shown by the blue line. And this is much closer than what we get with the default allocation. We tested AutoToken over hundreds of thousands of jobs in our production clusters, and overall the accuracy was quite good. The median error was 0, and the 90th percentile error was 50% or less than the default token counts. The coverage ranged from about 11% to 28% because AutoToken focused on recurring jobs only. And we also were conservative in selecting which jobs we want to predict for, because we want to minimize the cases where a job's performance could suffer if the predictions were not accurate. But in task, we are going to look at a higher coverage that we'll be talking about. So to recap, AutoToken focuses only on recurring jobs, and it tries to eliminate the over allocations for those jobs. That is, it goes from default allocation to peak allocation. But perhaps we can do even better by reducing the allocation even further and going towards a tight allocation. So that is the focus of the task project that Vishal will be discussing next.
Thanks, Saratajit. My name is Vishal Rohra, and I'm a software engineer at Microsoft. Let me walk you through our project task, which is short for token allocation for serverless queries. The previous project, AutoToken, focused on eliminating overallocation for recurring jobs. This project aims for a more aggressive resource allocation strategy, which we called tight allocation. So why do we need tight allocation? The first obvious answer is cost savings. And to measure the scale of savings, we looked at the cumulative distribution of potential reduction in jobs requested, tokens requested by scope jobs. Let's look at the figure here. The red curve is when the user does not want any change in performance, which in our case is the job runtime. As you can see, 50% of the jobs can request fewer tokens and still maintain the same performance. And the real value is for 20% of those jobs that can at least cut their request tokens by half and see negligible change in performance. And if the user is willing to take a 5% performance loss, the savings are even more significant. Apart from savings, as a whole system, tight allocation collectively decreases job wait times and increases resource availability. Now that we have validated the need for tight allocation, how do we help our users achieve it? At its core, given any job's compile time features, we want to predict the number of tokens that would lead to tight allocation for that job. But through domain knowledge and upon interacting with our users, we learned that optimal token allocation means different things for different people. Users prioritize cost savings or faster runtime based on the task at hand. So instead of recommending a single token count for a job, it will be more useful to predict the relationship between the number of tokens allocated versus job runtime. This should facilitate a more transparent process and empower our users to make an informed decision. And finally, from domain knowledge, we understand that the token versus runtime relationship is usually an exponentially decaying curve, which we refer to as the PCC, that is performance characteristic curve. So instead of predicting tight allocation, we want to predict the parameters A and B for the PCC. We'll explain what these parameters are in later slides. So let's look at the first crucial challenge in this approach. Our data, like the job graph, meta characteristics, for most of the historical workloads is only for a single token count. Users rarely experiment with different token counts for the same job. But to predict the token versus runtime relationship, we need data for multiple token counts so we can learn the trend for different types of job graphs. To tackle this, we introduce an efficient data augmentation technique, which we call ARRAYPAS, short for Area Preserving Allocation Simulator. We leverage past job skylines of a single token for a simulator that generates multiple skylines, but with different token counts. Based on a system level intuition, the simulator assumes a couple of things. First, the total number of computations, regardless of the number of tokens allocated, are constant. Then, if we discretize the skyline at 1 second granularity, a 1 by 1 square in the plot represents 1 token second. We assume these token seconds are also constant. And finally, the total area under the resource consumption skyline remains constant. Given these assumptions, this is how the simulator creates multiple skylines. The blue curve is the original workload skyline. And if you decrease the number of tokens, the orange curve represents the skyline for those constraints. The simulator is essentially flattening out the peaks and thereby proportionally increasing runtime, since the area under the curve has to be preserved. All of this significantly enriches our sparse training data. Now that we have enough training data, let's understand what does the runtime versus token relationship look like. Generally, there's a user expectation that if I provide more tokens, that would lead to lower runtime. While that isn't completely true, we have to acknowledge that the elbow region of the performance characteristic curve usually emerges before any sort of parallelism overhead kicks in. Since we mostly care about the elbow region, it's fair to enforce that we need a monotonically non-increasing curve. We enforce this by characterizing the inverse relationship between runtime and tokens as a power law, wherein the signs of the scalar parameters A and B are different. The goal then is to predict these parameters. This approach simplifies the problem and makes it easier for users to understand the trade-offs. Given that constraint, we tried a couple of different modeling techniques: XGBoost, feed-forward neural networks, and graph neural networks. And we evaluate each model by 3 criteria. First, whether the predictive curve maintains a monotonically non-increasing pattern. Second, the mean absolute error for the curve parameters. Third, the median absolute error for job runtime. As you can see, the first 2 methods, XGBoost smoothing spline and XGBoost power law, do not always predict a non-increasing curve. On the other hand, in neural networks and graph neural networks, you can enforce that pattern by design. Both the neural network models have comparable performance for curve parameters and runtime. GNNs, however, are particularly suited for this problem because the input data consists of a computational job graph. Also, XGBoost and feed-forward neural networks require the input features dimensions to be equal, while GNN is flexible and can accept variable feature dimensions based on the number of operators for the job. This can be seen in the results where GNNs outperform other models. And to feed-forward neural networks advantage, they take significantly less training time, which is more favorable for production. Now let's see how all of this ties together for the user. We piloted this project in an internal Python client for scope, and here's the expected user workflow. First, the user submits the job with the scope script and parameters like whether they want to visualize the PCC and if they have constraints around the number of tokens they can allocate. Then the job is compiled and a computational job graph is generated at the backend. We use that as input for our model and predict the curve parameters. Those parameters generate this visualization. As you can see, the user is able to inspect a given job's runtime based on different token counts. And if they aren't interested in inspecting this manually for every job, they can put this on autopilot and get an optimal token count, which for this case is 32, right around the time where runtime gains start to diminish. Ultimately, all this effort helps users make informed resource allocation decisions for all their jobs before it's executed. And this is the high-level system architecture of how this feature was integrated. On the top, we have the storage for job graphs, job characteristics, and the skyline. That data is cleaned and ingested. And in Azure Machine Learning, features are created, the model is trained, registered, and an endpoint is generated to consume the model in any environment. Our first environment is our Python submission system, which we showed earlier, wherein the query is submitted Compile time features are ingested in the required format, and the endpoint is called to infer the results. Now, I'll pass this back to Ratijit, who will dwell into another project, Auto Executor, which extends the work of task. Thank you.
Thanks, Vishal. Now we will talk about our last case study, which is Auto Executor. This is joint work with my colleagues at Microsoft, and this is work that is currently under submission. In this project, we look at predicting the optimal number of executors for Spark SQL queries for Spark and Azure Synapse platforms. Executors are processes on worker nodes, and each executor has a certain number of cores and memory that it can use. And by changing the number of executors that a query can use, we can affect its runtime and its cost, and hence it will also affect the resource utilization and provisioning decisions. So here in this project, we extend the PCC model in task as that Vishal just described. So here on the right, we see the runtime for a Spark SQL query from TPC-DS. The x-axis shows the number of executors and the y-axis shows runtime. And we model the PCC in two parts. The first part is the decreasing part, which we model as a power law function similar to task. But then there is a portion where the runtime flattens out, and that is the portion that we model with a constant function. So our PCC model is a combination of these two functions. And we take the maximum value that is obtained from these two functions. And here in these functions, A, B, and M are scalar parameters that depend on the query. And our approach is to use machine learning models to predict these PCC parameters. So use compile time and optimization time properties such as count of operators and input coordinates, average row lengths, etc. to the ML models. Here are some example predictions. So this one is showing a TPC-DS query, and the x-axis shows the number of executors and the y-axis shows time. The green line shows the actual time obtained by running the query at different executor counts. The blue line shows the predicted values with Auto Executor. And for reference, we also show the estimates from Sparklens tool. So Sparklens is an open source tool which can estimate the runtime for the query at different executor counts. However, Sparklens can do its prediction after one execution of the query. Whereas for Auto Executor, it was able to do the prediction before we could execute the query. So that's the difference. And as you can see here from this example, the prediction was quite good. Now, here are the summary results over the full workload. So here we take TPC-DS and then we split it up into 80% of training and 20% for test. And we do a 10-fold cross-validation. So F1 to F10 shows the 10 folds. And on the y-axis, we show the relative error. And we show the errors for different executor counts, 1, 3, 8, 16, 32, and 48. So for both Sparklets and Auto Executor, we see that the relative error is about 20% or less for higher executor counts, whereas the errors are larger at the smaller executor counts. However, from the PCC curve, we see that the elbow region, which is the interesting region of operation, is usually at the medium to higher executor counts. And so overall, this looks quite promising. So here is the overall system architecture. So when the query executes, we collect executor events and anonymized plans and metrics in our framework. And then there is a workload analysis phase, which then extracts the query characteristics and puts it into a workload table. Then there is a feature extraction phase that reads in this query characteristics from the workload table and then sends it to the model training phase. The model training phase trains the model using these features and the PCC parameter values on the training data. And then it stores the model in a database. When a new query arrives, we look up this model from this database, then score this model according to the query's characteristics, predicts its PCC, select the optimal operating point, and then request the optimal number of executors from the Spark engine. So this concludes our case studies, and we'll now summarize our talk. Our overall theme was the automatic selection of optimal parallelism for data analytics. And the reason why we do this is because we want to provide this capability of being able to select the optimal operating point depending on the cost and performance objective functions. And our approach is to use machine learning models that can predict the query's peak parallelism or runtime based on its characteristics. We'll now briefly talk about a couple of challenges and open research questions in this area. The first challenge is about modeling the PCC curve. In the auto DOP case study, we predicted the runtime for each DOP, and using these individual estimates, we can build up the PCC curve. In task, we looked at both pointwise prediction as well as directly predicting the PCC using a power law function as an approximation. In the auto executor case study, we used a power law function as well as a constant function to approximate the PCC. So the question is, are there other ways to model the PCC? And then what is the best way to model the PCC? The second challenge is about collecting training data. So for training the machine learning models, we need for every query, its runtimes at different amounts of parallelism. But this could be expensive to collect. So our approach on the task project was to use the Arepa simulator that Vishal described. It is using a skyline simulator to estimate these runtimes at different parallelisms. And on the auto executor project, we use the open source SparkLens tool, which is using a scheduler simulator to estimate the runtimes at different parallelisms. However, parallelism may not be the only factor that affects the job's performance. There could be other influential factors, for example, memory capacity, types of joins, etc. And then how would a simulator handle changes to those parameters? So having such capabilities in the simulator to handle changes to those parameter values as well would be very useful. Thank you for your attention. We look forward to receiving your feedback, and we are happy to answer any further questions that you may have.